Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample to say something about a population. A common application of statistical inference is using information from a sample to estimate a population mean value. So to do this, you first calculate a sample mean value, and then you put a margin of error around that sample mean that you calculated. So here you see the formula, mu on the left-hand side. That stands for the population mean, equals x bar, which is a sample mean. Again, that's something you could calculate. You could go out and collect some data and calculate a sample mean value, and then you put a margin of error around it. And we'll talk in more detail in a different video about the formula you use for this margin of error. Here's an example of what I mean by margin of error. So the average household income in Maine was $73,598 in 2017, plus or minus a margin of error of $1,747. The idea of the margin of error is this average household income value was based on a sample of Maine households, and if the Census Bureau had talked to a different group of people or collected a different sample, they probably would have gotten a different value for average household income, and this margin of error gives you an idea of the different values you'd get from different samples. Another common application of statistical inference is testing a claim about a population mean. For example, I might have this idea or make this claim that I think students study more than an average of 5 hours per day. So to test this claim, you'd first calculate a sample average. Again, I could go out and collect information on, say, a random sample of students and ask them how much they study per day. I could then calculate that sample average, compare the value from the sample to the 5 hours, which is my claim, and then ultimately I decide if there's support for my claim, or it's possible that I might reject my claim based on what I learned from the sample. In both of those applications, whether we're using information from a sample to estimate a population mean value, or we're using information from a sample to test a claim that we have about a population, we're ultimately using information from a sample of data. So therefore, a sampling distribution is very important. So in a second, I'm going to show you what I mean by a sampling distribution of a sample mean. But first, let's just look at the distribution of a variable. So this histogram shows you the distribution of Space Mountain wait times. Space Mountain is a roller coaster at Walt Disney World. On the y-axis, you see percentage of observations. On the x-axis, you see wait times. You see that the wait time ranges from pretty short waits of 10 to 14 minutes, all the way up to long waits of 135 to 139 minutes. And let's assume that this histogram shows the distribution of the population of all the wait times that could be out there. If we were to draw random samples of, say, 35 observations from this population, we could calculate a mean value from that sample. So you might take your first random sample of 35 observations, calculate a mean value, then take a second random sample out of this population, calculate a mean value, take a third random sample, a fourth, a fifth, a sixth, a seventh, etc. I mean, you could draw 100 or 1,000, say, random samples out of this population. And if each time you calculated a sample average, you would have, say, 100 or maybe even 1,000 or so sample averages, just like you can do for any other type of variable. You can take all those sample average values and plot it in a histogram. And this is what it would look like. So here we have what's called a sampling distribution of Space Mountain wait times. On the y-axis, since these are all average values from a sample, it's percentage of samples. And on the x-axis, it's the sample averages that you calculated. So the first thing you might notice is that the spread of this sampling distribution is a lot more narrow than the spread of the variable itself. For instance, we didn't have any random samples where the average wait time was 10 to 14, 15 to 19, 20 to 24, 25 to 29 minutes. Heck, there were only a handful of classes where we actually had sample mean values. So about 35 or a little over 35% of the samples that we drew from that population had a wait time of between 55 and 59 minutes. Likewise, there weren't any samples that had mean values of 70 to 74, 75 to 79, all the way up to those longer wait times. After making a sampling distribution, just like we would for any other type of distribution, we're interested in the shape, center, and spread. So first, we'll talk about the shape of the sampling distribution. And it doesn't matter what the distribution of the underlying variable looks like, the sampling distribution has a symmetric shape. For instance, you might have a variable that you're studying, and the variable itself might have a symmetric shape. If that's the case, the sampling distribution is symmetric. But it's also the case that even if the variable that you're studying has a very skewed distribution, the sampling distribution is symmetric. And that's thanks to the central limit theorem. Now, let's think about the center and spread of the sampling distribution. Well, the center of the sampling distribution is the mean value of the underlying variable itself. And the spread, which we call the standard error of the sampling distribution, is given by the formula of sigma subscript x bar. The subscript x bar reminds us that this is the standard error of a sampling distribution, and that is equal to sigma divided by square root of n, where sigma represents the standard deviation of the variable itself, and the square root of n is just simply the square root of the sample size. So in this example that we looked at a second ago, the sample size was 35, so that'd be the square root of 35. So let's go back to the distribution of the underlying variable, or the distribution of space, mountain, wait times. This is the population of all wait times. The mean value is 57 minutes, and the standard deviation is 29 minutes. So now we can go back to the sampling distribution of space, mountain, wait times. Again, this is showing the distribution of the mean values from these random samples of 35 observations. The shape of the sampling distribution is symmetric. The mean value is 57 minutes. Again, that's similar to the mean of the variable itself. And here the standard error is 4.9 minutes. That's found by taking the standard deviation of the variable itself, which is 29 minutes, and dividing that by the square root of the sample size, or the square root of 35.